Hi everybody, welcome to my 8th torsional bar video. In this problem, I'm going to solve the situation you see here. We're going to find and plot the internal torques and phi, knowing that this is a hollow sort of situation with a thickness t. If you want to know something else about torsional bars, feel free to check out any of my other torsional bar videos. So the first step that we got to do in this torsional bar problem is realize that it's pretty well the same as an axial bar problem. We're just using different variables. And you might want to notice here that something is changing as a function of x. So we're not going to use the discrete form of our phi equation. We're going to use the differential form of the equation, which is this. Okay, now this is a very generic form of the equation, because in this situation, not every variable is changing. All right, we're assuming it's made out of a single homogeneous material, so G is changing. And if you look, the torques applied are just here and here discretely, so it means in between in these sections, the torque is also going to be just a constant value. So we're going to write that the total displacement is the sum of the displacement of this piece and this piece. Or if you want to make it more accurate, it's the sum of all the millions and millions of little pieces up to this point. But since this piece can be described by one equation and this piece can be described by one equation, we break it up into those two sections. So I'll call this piece here phi angled plus phi straight for that little straight section. And then we can also write, plugging in this equation into these values, Alright, so notice here that I've automatically subbed in the things that are changing as a function of x. Alright, because this piece here, the diameter is changing, and we know that the polar moment of inertia depends on diameter, so that one's going to be changing as well. Alright, now I've kept G the same. I should probably call this solid. And then, of course, the internal reactions are different, but they're also discrete. So now, before we can solve for phi, let's go about and find the components that allows us to do that. So we'll find J. For each situation, we'll find the internal torque. So let's start with the internal torque. And the way we do that, like always, if we want to find internal torque, we need to expose the internal torque. To expose it, we need to make a cut. And here, since there's two separate situations, we make two cuts. One there, and one there. Alright, so let's look at a free body diagram of the straight piece. Okay, now just like we did before in axial bars, in this case we're going to sum up what's acting. In this case it's torques in the x direction to be 0. And it's quite easy to see that t in a straight piece is equal to t, which is not given to us as a number, as just given to us as some variable. Alright, so now let's look at the second free body diagram, this one here. I'll call it free body diagram of the angled piece. Alright, and the same as you did in the straight piece, sum of the torques to be 0. So T minus T by 2 minus TA is 0, or TA is T by 2. Alright, that's relatively straightforward. Okay, so if we wanted to move into plotting this like I was asking in the very beginning, it's pretty straightforward. Alright, T in the angled is T by 2, and T in the solid is T. Just like that. Alright, relatively straightforward. Now, let's move into the next component of this equation that we need to solve. We find internal torques for both of these situations. G is constant. Let's go and find the polar moment of inertia for each of these situations. Alright, now this is kind of a special case, this specific problem. Alright, because we know that the polar moment of inertia depends on area, right? The standard equation is J is pi by 32 d to the 4, alright? Or you can say J is pi by 2 radius to the 4, alright? These are equivalent statements. And we're using this one here because we're given the diameter in this case, alright? But in our case, two things are kind of weird, alright? We're told that it's a very thin-walled section, alright? So T is much, much, much less than D. So this thickness here, this little bit, that's T. It's very small. So there's a special form of the polar equation that we need to develop to deal with this. Okay? Another thing is it's changing. So we need to define what the diameter here is as a function of x. So that's the two steps we'll go through. Let's first find the diameter as a function of x. So looking again at that first piece here, I'll just pull it up on the very bottom here. What we want to do is find the slope of this piece first, alright? And we know that slope is rise over run. And in our case, it's negative. And let's just define the x-axis to be right here at 0. So we'll find radius as a function of distance, and then just times it by 2 to get the full diameter. So the rise, that's just going to be from d then, alright, because it starts at 0. And since it's half of the distance, and this is 2d, it starts at d, and this is d, so it's going down to d by 2. Okay, so rise is d minus d by 2 for run, starting from the same point, 0 minus l by 2. Alright, the distance it's gone over, that's l by 2. And we can simplify that to be d by l. Alright, now we know that this is a linear slope, and anything that's linear can be described by the equation y is equal to mx plus b. So we'll plug in our m and our b, that's our y-intercept. So taking x to be 0 here, our y-intercept is just going to be d, half the distance here. Okay, so y is equal to d by lx plus d. Okay, well this is not y in our case, it's actually radius. Depends on x, so its radius is a function of x. And we know that diameter is twice the radius, so timesing this whole equation by 2 will give us that.